for Good, the leading United Nations platform on artificial intelligence. Organized by the International Telecommunication Union, the United Nations Agency for in partnership with over 50 UN agencies, and co-convened with Switzerland. The mission of AI for Good is to unlock AI's potential to serve humanity. As a multi-stakeholder platform, AI for Good advances solutions, standards, and skills. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging session. Boost your AI skills and elevate your career with the AI for Good Discovery Badge. Receive verified digital credentials that recognize your engagement in cutting-edge sessions, exploring how AI is being used to tackle global challenges. To see if a session is eligible, look for the blue badge banner on the right side of the video interface that activates at the end of each live session. Share your badge on LinkedIn and across your professional profiles, and check the AI for Good Events webpage for upcoming eligible online sessions. Discovery Badge sessions are part of the AI Skills Coalition, ITU's global initiative to strengthen credible AI learning pathways and expand access to high-quality, trustworthy AI knowledge worldwide. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor.
Hello everyone, and welcome. My name is Paweł Gmyrek, and I'm a senior researcher at the ILO's research department in Geneva. Thanks for joining us today for another session of AI for Good on AI and work. It's the thematic series of discussions moderated by the ILO and jointly hosted by the ILO and ITU. And there are three ways to follow this discussion today. You can watch us on the neural network of ITU, where you will be also able to ask questions live. You can watch us on the ILO's live channel, where you cannot ask questions, but you can also see this video recording there later, as well as on YouTube channel of the ILO, where you can also see the recording afterwards. And the idea for today's session is to talk about the big picture of AI's impact on economies. That is very much because a large part of the discussion so far has focused on micro-level impact. For example, on exposure of occupations, who is affected, which tasks are at risk, and what happens at the firm level. But the bigger question is what really happens when these effects scale, when AI starts to reshape the economy as a whole, and what happens when productivity, output, prices, and wages start to adjust, how this might affect economic growth or employment levels. And one way to do this is to model the entire economy as a system and to compute mathematical formulas on how such a system is structured, how it achieves its equilibrium, and how this equilibrium might adjust when an external shock emerges, for example, due to an impact of a new technology like AI. And that's what a computer general equilibrium model attempts to do. Today's discussion will introduce such a model, which is managed by the World Bank, and we will discuss how it can be applied to a concrete economy, in this case to Poland, which is also my home country. And I'm here today in the role of a usual moderator from the ILO, but also a collaborator in this research project, which incorporates the ILO-NASK index of occupational exposure to generative AI. And I'm very pleased to be joined by three colleagues from the World Bank Group who will present the model. The first person is Ludwig Mittig-Bejene, the senior economist with over 15 years of experience in macro-micro modeling, and who holds a PhD in economics from the University of Nice Sophia Antipolis. The second speaker is Natalie Piccarelli, a senior economist working on macroeconomic and fiscal policy and innovation in AI in Europe. And Natalie has a PhD from London School of Economics, as well as degrees from Columbia University and Sciences Po. And our third speaker today is Markus Kitzmüller, the lead country economist for the European Union at the World Bank. Marcus has a PhD from the European University Institute. It's a real pleasure to have you here. And with this introduction, let me hand it over to you for a presentation, which as usual will be followed by a discussion.
Thank you very much, Pavel. I think I'm sharing the slides. Yes, perfect. So thanks, Pavel, for the introduction, and everyone in AI for Good for having us. We're very excited to be here, and the work we're going to present today is the result of more than a year and a half of collaboration with a large research team. Everyone is on the slide, and there's even more people that have contributed. And as you mentioned, it's a collaboration with you at the ILO, with the Lukasiewicz Research Network in Poland, with the Ministry of Finance of Poland. And we also wanted to particularly mention Professor Groviec from the Warsaw School of Economics, who has been really great throughout this process, advising us. And so what we're going to present today is really first, so the agenda is what we're doing when we mention that we're measuring the macroeconomic impact of AI and why, how we're doing it, and what are the results that we're finding. So we started with the premise that AI is transforming economies at an unprecedented speed. And at the same time, the questions for policymakers are rising far faster than the tools that exist to answer them. So what's the impact on employment? Which sectors are going to be touched? How fiscal revenues are going to be affected? And the World Bank group is not only a lending institution, it's also a knowledge bank. And so we ask ourselves, can we develop an open source tool that can help policymakers answer this? And what we're going to present today is really, yes, we think we can, and this is what we have developed, what we call AI Manage, which is the computable general equilibrium and model, and Lulit is going to go into details of what this means. And as you mentioned, the first application is to Poland. It was developed jointly with Polish institutions, and practically because it's an economy that is asking itself, what's the path of AI diffusion, what's the impact on jobs and firms, and what policy choices can we make today? So there's a lot of empirical literature that, not a lot, there's a wide array, I would say, of empirical findings of what the impact on jobs is from AI, right? So from Acemoglu's more pessimistic view to Agion's more optimistic one. And what we're doing here, and what we have this piece in the slide, which is a publication in the Peterson Institute from Anton Korinek and his colleague at the IMF, is really to say that under deep uncertainty, we are here not to make a choice, but really to model different scenarios. So we're not really expecting to be part of that debate, but really to provide a tool that can help under deep uncertainty policymakers make choices, given how much they can model different scenarios of AI. And we think this is particularly important with AI, and I think everyone hearing that might be connected today is familiar with this, but particularly because it's not just another technology, right? It's a general purpose technology that has the potential to trickle down across sectors. And so that you have to take into account the whole of economy effects, as Lulit is going to explain in a minute. It has the potential both for automation, augmentation of labor, so it both can displace and complement labor in ways that other technologies have not in the past. And then also at the same time, there's the potential for cost reductions in compute, while the capability gains have also exponentially grown. And so that really cannot be captured just with a linear TFP shock. And countries are also at different stages of the value chain on AI, right? So that's also important that it's country specific, because very few are at the upstream level, like the US and China, that with foundation models, and Poland would be more downstream with like exporting eventually ICT services and AI services. and the development stage. And finally, deep uncertainty that characterizes it is another characteristic that I've already mentioned. And so that's why we think a computable general equilibrium is really a good tool to develop.
Okay. Thank you, Pavel, for having us. So I will present briefly our approach. So as Natalie has given you the context, our objective is to quantify the potential macroeconomic impact of AI. And in doing this, we have selected to use a general equilibrium whole of economy perspective. So in this perspective, the different agents in the economy, so that is firms, households, the government, and the rest of the world, are represented within this framework, but not only represented, but they also interact. So what does this imply? It implies that policies or shocks do not affect just one market or just one agent in isolation. Prices will move, resources can be allocated either within sectors or between agents, and finally, budgets and resource constraints can be binding. So in this context, it's interesting to look at this question from a general equilibrium perspective. And finally, it's also important to be able to capture the distributional effects, looking at the different sectors and the different workers in the economy. Within the general equilibrium framework and models, we have computable general equilibrium CGE models. So what are CGE models? Like any macro model, it's a system of equation. So in this system of equation, we operationalize the general equilibrium theory by calibrating this model and the set of equations to real economic data. So this data is represented in a social accounting matrix, and this social accounting matrix represents the different transaction flows that are represented in a system of national accounts. And the system is solved numerically, hence the computable part of it. Now, looking at the core features of CGE models. So essentially in CGE models, we have the different agents that we just saw, but we have two main agents that have an optimizing behavior and their optimization decisions. So that would be for households, it will be a maximization of utility, while firms will maximize profits under budget constraints or technology constraints. But this framework has to be also consistent with the macroeconomic constraints and the macroeconomic conditions that are underlying them. So in this sense, it's a framework that allows us to trace representative agents, but also be able to capture the macro aspect. So the equilibrium part obviously represents that supply is equal to demand, and depending on the model, obviously you will have a slow or a fast adjustment of prices in order to be able to have this equilibrium. And maybe one point to note here is when we talk about equilibrium, it doesn't mean that all accounts are balanced. So macroeconomic imbalances, so this could be in the fiscal account, it could be also in the current account. Those are represented and they actually really matter. So in our macro model, in our CGE model, we have a detailed depiction of sectors, but also factors. Okay, it's a dynamic model, and that makes it interesting because we're able to trace some of the dynamic effects that can occur. And finally, it's important to note that a CGE model is not a forecasting model. It's a simulation model where we compare different types of scenarios against a baseline that has been calibrated, replicates the historical, but also shows the projections that come from forecasting models. So in sum, it allows us to analyze policies in an economy-wide framework. It helps us to quantify, but also trace who can gain and who can lose from different shocks or policies. So this is a very brief overview. It's a sneak peek of what manages. So again, I said it's a system of equation, and these are organized in blocks. A few extensions have been included and others are underway, where we are trying to improve our specification. And when we talk about how agents are interconnected, and you can see this from the node view of the managed user interface. okay, where you have the different macro indicators, but also the different institutions and agents that are interacting. So what does this mean? It means that a shock will have a direct effect, which we are able to capture usually with a partial equilibrium type of analysis. But this type of model also allows us to capture the indirect effects and induced effects. Okay. So then the question is, why do we need a new AI manage? And the answer is relatively simple. If you look at what standard CG models, including manage, can do, is they help us capture quite a lot of things within the same framework. So what do? They can they allow us to analyze sectoral spillovers. Input-output linkages are important, and are able to help us in understand how sectors are linked with each other. They can capture macro structural changes. They can also help us assess fiscal and trade impacts. And finally, they also allow us to simulate forward-looking scenarios that span over time, over 10 years, 20 years, or more when necessary. What they cannot do, to the best of our knowledge, is within the same framework depict tasks explicitly, especially by distinguishing between cognitive and physical labor. The second point, which we think is also very important, is to be able to represent software capital. So most of the models we've come across tend to simulate AI or represent AI as a TFB shock or capital deepening scenario. Within the same framework, it's also rare to find CG models that capture heterogeneous exposure, so across sectors, but not only across sectors, but within the same sectors, different occupations that could have different exposures to AI. And finally, two other important aspects that we think are missing within the same framework and CG models is the distinction between automation and augmentation effects of AI, and finally, the explicit diffusion dynamics. So that's why we set out to build or to extend the managed WB framework. And how we do this is going to be presented in the next slides. Now, this is not an easy task, as you can imagine. So the first step in our approach was to have some clarity on what we mean by AI and how we measure it. So in terms of the concept, we follow Acemoglu and Restrepo's definition, where AI consists of software systems and trained models that use data-driven methods. So once we have this concept, we still had to measure it. So we had to identify some entry points in our data. Our data is a social accounting matrix. So essentially, you will have different sectors and different products. So the way we define it is actually relying on the definition of AI that is in the UN System of National Accounts, the 2025 accounts. And we also rely on OECD various papers that give directions on how you could measure AI in the economy. So essentially, it enters in two places. One is AI is considered as a flow, and where you find it is in the intermediate as an intermediate service. So when firms purchase AI capabilities from external providers, so these will be found as intermediate consumptions in IT services, in software and data processing. So these can also be imported. That's why you have the cross-border purchases that are also considered. But AI can also be an intangible capital when firms acquire AI systems for a repeated use for a period more than 1 year. So again, you can see these flows are registered as it's a stock, but the flows are also apparent in the investment in the GFCF under software and intellectual properties. So once we have defined this, the next step is, okay, we have some clarity on how we can measure AI, what are the entry points in our data set, but we were under the impression that our standard managed model was not ready to be able to capture the different entry points. So essentially, going back to the concept, AI is likely to augment or substitute workers. So in that sense, what we do is we come up with a new production function where we introduce the hardware-software framework developed by Grovik, Jablonka, and Patreka. And this is a very interesting framework where in a standard macro model, output is produced using labor and capital. When it comes to AI, it is more interesting to be able to distinguish labor between human physical labor and human cognitive work. So following the Grovik and co-authors approach, we redesigned our production function such that now it relies on a feature where output is produced using hardware. Okay, so hardware combines human physical labor and physical capital. These two can be substituted with an imperfect substitution elasticity. And at the same time, it also uses software, and software is a composite of human cognitive work and digital software.
Right. So then the question is, how do we translate this from the theoretical framework into our managed model? And so what we have here is the nested CS production function, which is really the engine of our model. And just in other terms, it's how firms in the model combine inputs to produce outputs. And so basically total outputs is both intermediate inputs that firms buy to create value added. And here the big difference is that, as Lulit mentioned in the previous slide, value added is going to be produced by these different production factors compared to traditional capital and labor, which is hardware and software. And so here on this hardware, on the green side, we have the hardware nest, which is this green tree here that you see, which is basically the combination of physical labor, human physical labors, and physical capital, which is the muscle of the economy. And then we have the software, which is human cognitive work and AI software. And we do this for 22 sectors and 9 occupations. So basically, we rebuild the sum to have 22 sectors of the economy and across 9 occupations using ISCO one-digit level occupation. So, for example, here we can imagine it's a representative sector. And so in this sector, so for example, agriculture or finance, and then it's divided across the 9 occupations. And what we need to define to be able to use the nested CS production function is the share of work that is attributed to physical labor and the share of work that is human cognitive labor. At the same time, then we have physical capital on the hardware part, and as we mentioned, the AI software part, which, as Lulit explained earlier, we quantify here as both the consumption of intermediate services of the data software and ICT sectors, and then the investment on AI intangible capital. So you need a combination to produce in this economy. And what will be important for us to define, and what's going to be really the key question is what's the relationship between human cognitive labor and AI software, what we call sometimes the AI software bundle. Basically, as AI diffuses, as its cost is reduced, then how much are human cognitive work going to be either augmented or automated, and this is a relationship that we call basically an elasticity of substitution. But before that, basically, you might be asking yourself how we define what is a physical and cognitive share of labor. And so we start by the task content of occupation. So following very much the literature that occupations are a bundle of tasks. And here what we do is at 4-digit level, it's called digit level, we train an LLM to define whether the task content of occupations are mostly physical or cognitive. And from there, we aggregate up at the 1-digit level, which will be part of our 9 times 22 matrix. And here what you can see, and we weight by the employment shares in the Polish economy, so it's representative of the economic structure of Poland. And here what you can see is basically the average, and you can see at ISCO 1-digit, which is basically managers, occupations that are manager are mostly cognitive in nature. professionals as well have a high share of tasks that are cognitive. And on the opposite end, you have elementary occupations, plant and machine operators that have a higher share that is considered physical. And we do this specifically for every sectors, but here what we're showing you is the average for the economy. And once we have this, the key question becomes, how do we model, how do we create this elasticity of substitution between human cognitive work and AI, right? And for that, as Pavel already mentioned, we're using the work that has been done by him and co-authors to create this based on the exposure gradients to GenAI. And maybe Pavel, you want to come in to explain what you do.
Yes, thank you. So that's where I switched from moderator to contributor for a second. And this is probably a slide that I have shown the most in the last year. It's an index of exposure of occupations to generative AI. Each dot that you see on this plot is one occupation in the International Standard Classification of occupations, which recognizes 436 occupations, more or less, and assigns tasks to them that allow us to compare that an occupation of a primary school teacher is the same occupation across countries. By doing that, we can see that based on what people do at work, they sit in the same occupations. And essentially what we do, working with NASK in Poland, which is a research institute under the Ministry of Digital Affairs in Poland, we started with a Polish classification, which is even more detailed. It's at 6 digits. So it's 10 times larger number of tasks. And we assessed each of these tasks we assessed the extent that each of these tasks could be performed using AI, the type of AI that we have now, like generative AI. And when we group it to occupations, you end up with this plot, which uses 2 moments of distribution. You have the average occupation on the horizontal line, and on the vertical, you have the standard deviation, so the measure of dispersion of scores for each task within each occupation, for tasks within each occupation. And as you move from these gray dots on the left to the right, you increase your exposure as an individual occupation to AI. So when you are in those gray dots, you're mostly in manual occupations where you're quite unlikely to be automated, let's say, or your tasks are unlikely to be automated by generative AI. But as you move into the green and blue zones, you increasingly have more and more tasks that could potentially be performed with this technology. And once you reach the far right, so the red triangles, you are now in occupations where majority of tasks receive a high score of potential substitution by AI. And also these scores are not really dispersed, they're concentrated. So majority of the scores in that occupation are basically stand for high exposure. So you're much more at the risk of automation. And that gives us 4 categories of exposed occupations, which start with those blue dots and go to the red, and a sort of gradient measure of exposure across all occupations that are typically used in occupational classifications.
Basically, and we use this to create the elasticity of substitution. So let's show you how we do this.
Okay, so so far we have presented to you why we want to use an economy-wide model. Then, in order to operationalize the economy-wide approach, we decided to work with the CG model, and we adjusted the approach, so the equations in our system, in order to be able to capture, at least to have entry points of AI. We also disaggregated significantly the labor segments in order to be able to distinguish cognitive work relative to physical work. The next step is taking into consideration Pavel's exposure scores. So obviously, exposure scores are not directly implemented in a model. So we needed to go from these scores to elasticities of substitution between cognitive work and AI capital. So the way we do this is by taking the list of scores that are classified in now three groups. You have the not exposed, the ones that are exposed but likely to be augmented, and within Q3 we have the ones that are highly automatable. But we needed to decide on what should be the value of the elasticity of substitution between AI and cognitive tasks. So for this purpose, we rely on Kaunendo and co-authors' empirical estimations, and so based on their estimations, we are able to use a logistic curve where the upper bound is set at 2.18. Okay, so and then the lower bound is going to be below 1. Okay, but at least on the inflection of the curve, we rely on the professionals, which have an elasticity of substitution between labor and capital of 0.86. So essentially, this is how we go from the AI exposure scores to the elasticities of substitution between cognitive work and AI. And for those that have minimal exposure or that are not exposed, we use similar elasticities of substitution as physical labor.
So basically with that, what we do is that we create this relationship, right, between augmentation and between cognitive human work and AI software, and how much they are likely to be substituted or augmented. But the augmentation part, what we use is really an AI factor on top of it, right? For those occupation sectors that are likely to be augmented, then we have this AI factor, which we call the labor productivity potential or frontier, which is basically creating a ceiling as how much labor productivity in a given sector occupation would increase over time if it was to be augmented. And so there's no augmentation in the baselines as workers have the same effective productivity without any AI shock. But as firms start accumulating AI capital, the factor raises gradually towards that potential. And each sector has a maximum, and we define this both using empirical work, the theoretical literature, and anchoring it in the ICT revolution of the 90s. So we wanted to check whether our ceilings were what would be the equivalent in historical terms, what had happened during the ICT revolution during 10 years, and whether it would fit. So here what you can see in the figure is for different sectors, right? Agriculture over time still has a very relatively low labor augmentation potential because it's less exposed to AI and because of the characteristics of the sectors, and IT services is at the top end. And here, for example, what you see with the purple shadow is the maximum ceiling, right? Which is 1.32, which means that in IT services, we could expect, at least in our model right now, that labor productivity could have a ceiling of 32% higher cumulative over 10 years if AI augments, if AI adoption is diffused fast enough in the economy. And so this may seem large, but in reality, compared to the ICT boom, it's relatively conservative, just to put it in perspective.
So the last part of our modeling exercise, but also this is part of the scenarios, is to think of the technology frontier. So one could simulate an increase in adoption by assuming that the technology frontier does not evolve. So in our case, the intuition that we have is that we have seen that these AI tools have been improving in their capabilities at a very fast rate, and we wanted to be able to represent this in the model. So the way we do it is through an increase in efficiency of the AI software bundle that we have, but in the absence of information on how fast these technologies are evolving, we rely on two assumptions. So one is a 5% annual gain, and the second one is a 10% annual gain. So this increase in efficiency affects all the sectors uniformly. And so we compare it with no technological frontier improvements in our simulation.
So let me just talk to you about the last two, the last important parameter here in our model before we can finally show you some results of what we get. So basically, here it's the adoption and diffusion scenarios. So we use as an AI adoption metric a firm level adoption using Eurostat definition of firms using at least one AI technology, and so. Right now, for example, in Poland, this is relatively low. For the average for the economy is about 8%. Of course, we know this varies by firm size and different by sectors, and you can see that in the right-hand side where we have some AI adoption rates by sector in agriculture, construction, and finance, and IT services. The dotted line is what it's today in 2025. So in agriculture, it's 2%, but already in finance and IT services in Poland, it's about a third of use of AI technologies. And so here we're going to define the baseline, which is very important, which is basically keeping that 2025 level over time, imagining that there's really no change on AI after 2025. And as Luigi explained, then in our model, what we do is that after having that baseline, we will compare different AI adoption diffusion scenarios.
We cannot see the slides. I'm terribly sorry to interrupt you, but they switched off just recently. So if you're able to reshare the screen, that's...
All right. I stopped sharing and reshare. So I can see them on my side.
Yeah, now we can see them. It's perfect. Thank you.
Okay, perfect. All right. So as I was saying, so we have the baseline, which is really important, which is against what we're going to compare everything in the model, right? So we're going to then try to have different AI diffusion scenarios. And so based on that, we will see what's the impact on GDP, on employment, on the fiscal accounts, on the current account, and so on. So this is our baseline first, and then we will model two different AI diffusion scenario, a high adoption scenario and a mid adoption scenario. The high adoption one is really trying to push Poland to where EU frontier countries is today. It would get to about 32% of the economy on average by 2035, which is the horizon that we're using for modeling. And with sectors that are very different, right? In IT services, it's about 75. It means 74% of adoption by the end of the period. In agriculture, it's still 11%. And then a mid-diffusion scenario, which is really the half of the growth rate of the high adoption one. And what we do is that given our AI bundle, basically, the shock is that the AI bundle will increase at the projected rate of adoption. So either the consumption of intermediate services of AI and of data and software, or the investment in AI intangible capital. And finally, before the results, and this is really the last one before, is the net labor market effects, right? So here, what we will show you is both the impact on growth, but also the impact on labor markets. And what we have is different channels. The automation channel that we are all aware of, where AI replaces labor in specific occupations, and this is captured through a reduction in labor demand, both through quantities and prices, so wages and labor demand, jobs created. Aggregate employment generally falls for this when this channel is in place, unless output growth compensates. And this mostly will apply to high exposure sectors, which are more routine, codifiable, and rule-based, gradients 3 and 4, more in the models we already present. Then we have the augmentation channel, which is linked to this labor productivity frontier or potential that we have, where AI raises the effective productivity of remaining labor. And here we see two different mechanisms at place. One that we call expertise leveling, where we see an increase in jobs and an increase in wages at the same time. So these are new jobs created. And this is dominant for physical workers and cognitive non-routine occupations in most sectors. And then the other ones is what we call expertise reducing, where we have an increase in jobs, but the wage is reducing. So the net effect will really depend on how much these are leveling up together. And we will show you the nuances across sectors, right? And we test 3 different scenarios of mobility, of labor mobility, meaning how much actually labor and workers can move from one sector to the other. And one of imperfect mobility, which is closer to what we imagine frictions in labor markets that exist today in Poland and in other countries. One of perfect mobility, where workers can really reskill and adjust and move to other sectors. And one that is within occupation sector specific that we're still working on based on the task, the task similarity of occupations. So basically, what are the results?
So today we will be presenting the results on the high adoption scenario. As Natalie mentioned, we have multiple scenarios, but it would have been too busy to present it at this stage. And we will focus on the key indicators, that is impact on GDP, decomposition of the drivers of growth. We will then look at the sectoral level and then move on to the effects that we find on employment. So what you see in this slide is the deviation in percentage of GDP relative to its level in the business as usual scenario, that is the adoption stays at 2025 level. And what we can see is that all scenarios show that GDP is likely to increase, to expand. The lowest result is registered in the low mobility scenario, where labor market frictions are very strong. As we release these labor market frictions, the GDP gains tend to increase significantly. And finally, when we add the improvement of the technology frontier, the impact nearly doubles from the no technology, or at least no technology scenario. When we decompose our results, unsurprisingly, we find that, and this is again, these results are showing the deviation from the baseline in percentage points. And we can see that TFP is the dominant driver of growth, okay, whether it is in the short to medium term or in the medium to longer term. 2 other striking features are the increase in the contribution of software capital, which is not surprising because we have adopted the hardware-software approach, and higher AI adoption implies higher AI software capital. We also have a relatively small but positive contribution of physical labor. Now, if you look at those that are contributing less to growth, you will see that capital is becoming a drag to economic growth, and this is because there is some level of crowding out of investments towards the software component of the economy and a little bit away from the capital component. And it is the software component that also benefits from efficiency gains. And finally, cognitive work contribution to growth is declining relative to the baseline. And between the high adoption with and without technology, the results tend to amplify, but the direction is maintained. Now, if we look a little bit deeper into our results, you have seen from our previous slides that sectors do not have the same exposure to AI. Okay? Sectors do not adopt AI at the same speed and at the same level. And sectors differ because they have different structures. Okay? The structure of the production is different between computer and programming services, for example, if you would compare it with the manufacturing. So if you look at the right-hand side of the panel here, we are showing the contribution of these aggregated sectors to value added. And the biggest sectors, as you can see, are manufacturing and wholesale and retail trade. So overall, our results indicate that value added grows in all the sectors except 3 sectors. The gains from AI are not equally distributed, and unsurprisingly, the computer programming and information services, which are also the providers of AI services, although AI services are also imported, tend to expand relatively more, and those with higher exposure expand more. The last sector where you see a notable decline in value added is the real estate. So this one is a non-tradable sector, and its demand essentially comes from households for which demand or income and demand has declined. So those are the main results that we have at the sector level.
And so now what we wanted to show you is also the other side, right? What happens to employment? While the economic growth grows in the different scenario, employment rate as a deviation from the bow, again, percentage points, does decline. So labor demand declines, and it's different depending on the high mobility scenario or low mobility scenario. The ones where there's higher losses to jobs, it's really the low mobility scenario here, but also a higher mobility with higher efficient technology. And this is basically because there's less on the first one, because there's more frictions on labor market that allow less movement across new jobs or jobs that have more reskilling. For example, there's less reskilling options and so on. And then on the technology efficiency one, it's mostly related to the fact that automation and substitution becomes a higher predominant force. But so now the idea is to show you what happens at the disaggregated level, right? And here we will do this in two ways. First, to show you the percentage change in each of the sectors. So the sectors are again on the left hand side. And here, the colors of these bars are really the different occupations. So you can see that the highest losses are really for professional services, finance and admin support in terms of overall changes in quantity of jobs demanded. And this is for the high mobility one without technology efficiency, and particularly for professions that are more cognitive, more routine or more codifiable in nature. We have professionals, technicians, clerks, and managers overall that are more affected here for these three sectors. And some sectors do have a gain again on the other side of the line that you can see with the green and purple colors and pink colors. But overall, it's mostly, we can see that the negative impact on cognitive labor, and which is also reflected on the contribution to growth that Julie just showed. So to give you the other side of the coin, this is what happens to physical labor at the same time, which is basically where there's an expansion of jobs. But these are actually expansions that are quite insignificant overall. So if you see on the gray bars on the right, for example, professional services on the physical labor occupations and sectors increases significantly, but this represents only 1.1% of physical employment and physical labor employment. And so there's an expansion, but at the same time, and here is the high mobility scenario where we can imagine a higher reallocation of labor across sectors and even between the physical and cognitive occupations. But it's not as high, at least in this moment. And the final results we wanted to show is really this figure that brings a little bit everything together. Here is really the impact of AI back on cognitive labor, trying to show you both the impact on prices, so wages on the vertical axis, and then on the horizontal one, quantities. So here is our four categories that we find. So on the bottom, you can see what is the result of automation. So mostly where sectors and occupations where we see a decline in wages and a decline in labor demand. And this is mostly the occupations. And here again, the circle around the dot is the occupations, and otherwise the dot represents the sector. And so this is mostly the sector occupations that are more highly cognitive in nature. in terms of in more routine, more codifiable, and so not surprising. It's what, and also those that have higher adoption, higher labor productivity frontier, and not surprising, we find like finance, ICT, professional science, and technical occupations. And so this is mostly that quadrant. Then we have the expertise reducing quadrant here, which is the sector where we see a decline in wages, but at the same time an increase in labor demand. And here are again occupations that remain relatively more routine and codifiable, but where there is also those that are a bit less routine in terms of cognitive. And finally, we have the two blocks on the top, which are the more positive ones, which is basically where wages increases and either quantity demands, where we call the expertise leveling. And here it's mostly occupations that are the 5 on the legend on the left, which are a little bit more less routine than others, and in different sectors than, for example, also we have here ICT and finance, but these are different types of occupations. Then we have the new jobs, and the new jobs are mostly related to what do we find in new jobs. It actually, we cannot really disentangle what this means, right? But it's sectors where there's an increasing wage and an increasing labor demand. And either this can be because new type of jobs are created, or just because there's an expansion in the sector, because the sector is growing, thanks to, for example, labor productivity gains, also. So we wanted to quickly show you what happens with the technology is able to have higher technological efficiency over time. So with the 10%, and what you generally can see is here it's a shift to the left and to the bottom, and the percentages are much more alarming. So just for the sake of the figure and the discussion, what we see is that again it's the similar pattern, but what with a higher impact basically on automation and expertise reducing for some of the jobs, and at the same time for those that have the expertise leveling or new jobs impact, it increases a little bit higher. And so with that, I think we are ready for a nice discussion together. Yeah.
Great. Thank you so much for this presentation. It's a slightly longer session probably than what we normally have, but it's also the complexity of the model that justifies it. And I wanted to ask right away and open a discussion asking about these results you just presented. So, of course, it's not a projection, it's a scenario, as you highlighted, and we are presenting the most extreme scenario in this case. Yet it's dramatic for cognitive work, right? Because we see drops in cognitive employment basically across the board, and the new occupations that are showing up as maybe even new jobs are in construction, manufacturing, very much manual jobs. So I'm wondering how that squares with the concept of new tasks emerging and new occupations emerging with technological transitions. So in the past, that's a well-known argument, also substantiated by the research, for example, of David Autor, or by the recent arguments put forward by Acemoglu, Autor, and Johnson, who basically argued that each new technology, yes, it eliminates certain jobs, it transforms many jobs, but it also creates a lot of new occupations, new tasks that we couldn't even imagine would exist today. For example, what happened with internet, which generated a whole range of new occupations that no one imagined would exist. How is that treated in the model? And is it modeled at all, or is it something that applies to today's employment, these jobs that we're seeing in today's employment, and these are things that, again, we are unable to predict as this technology diffuses into the economy?
So maybe, Pavel, I start us off on this question, and thanks a lot for having us again. So let me start by saying that on the one hand, when you look at the assumptions that drive the dynamics in this model, you may still be saying that because you say we are looking at an extreme scenario, right? Our adoption scenario at 33% by 2035. Some people may say this is still a very conservative scenario, right? And also the same goes if you remember our technology or technological progress parameter at 5 or 10% may still be at the lower bound given how fast AI gets more efficient. So just to set the stage, right? On the one hand, yes, we call it a high adoption scenario, and you may call it like an optimistic scenario or an intense scenario for AI adoption, but it still may be at the lower bound. So having said that, to come to your question, new tasks, right, and new type of jobs in the qualitative sense are not explicitly part of the dynamics in this model. So I think we are bound by the structure that we have, and it's a very detailed structure, as Lulit and Natalie have presented. In Poland, we have very detailed labor market data, occupation data, task level data, but we are unable to capture the creation of new tasks, right? And therefore the emergence of new professions or new types of activity. However, if you remember the slide that Natalie showed in the end, there is a part of professions and tasks that will grow, right, in terms of demand and in terms of productivity. And so in a way, there is new jobs that will be created. It's just that it shifts between combinations of existing tasks. So I would say like that, to some extent, we are capturing new jobs becoming more prominent and new sectors getting more weight, but not the qualitative creation of new tasks. That's how I would describe it at this point, but it's definitely something for future research to consider.
Thanks, Marcus. And there's a question coming from actually my colleague at the ILO, from Rosanna Merola, who is asking about the modeling framework, largely assuming basically a competitive market. But in contrast, what we're observing is that AI creates market concentration and persistent trends, she's saying. So we have those superstar firms that are one take all, and they have persistent trends and then monopolistic power. And she's basically asking whether the model doesn't distribute too evenly the gains across firms that are being modeled. And I guess a second part of that question, also from my side, is the role of institutions. So in addition to market concentration and maybe an uneven distribution of gains, how does the model think of labor market institutions that also shape the policies and regulations around how adoption actually occurs? And would that change the findings of the model? Is it modeled at all, or is it possible to model that, or is this a scenario without the institutional role that we are discussing at this point?
Right, so maybe I can start on this. So yes, I think that's a fair point. So the model is really on perfect competition. So we don't really have here monopolistic competition. We have an alternative one with endogenous technological change that features monopolistic competition. But in this one, we don't. At the same time, in Poland, Poland is it's mostly an importer of AI services, and it would not reflect necessarily the same type of it will not, the kind of foundational models, the ones that have the higher concentration, will be impacted mostly to the imported prices, right, rather than anything else. So it wouldn't affect as much as I would say. In terms of institutions, yes, I think, of course, the model has its limitations, and we are not capturing every detailed institutions. What we can do and what we have shown is a little bit considering, for example, labor market frictions, right? So if we have lower labor mobility, it means that there's more frictions, and there's like, for example, less reskilling options, there's less mobility due to these labor market institutions. And that's what we can do in the model, make these assumptions, for example, to take institutions to a certain degree into account.
Great, thanks for this. We are kind of running out of time, but I want to ask you one or two more questions. There is Melanie Engler who asked in the chat about the macroeconomic impact in the Global South. And basically, I know that, I mean, we were discussing this is the first application, an attempt to adjust it to the economy of Poland. But I know you have in your plans to then adapt this model and try to use it in other countries. And I want to ask about the possibility of using this model in lower income economies and where you see limitations. Do we hit, a limitation of data availability, which often is a problem in lower income economies? Would it be equally applicable? And maybe on this note, also, I wanted to ask you more about the uptake of these models historically. To what extent do local authorities use them? Is it used for policy discussions? Have you seen these scenarios being close to what actually materialized in the past? In reality, maybe you could tell us about that a little bit before we close the session.
So maybe I can come in on the model and how easily or it can be replicated or expanded for other countries. So the way we have developed the model right now is in view of being able to implement the same type of analysis for various countries. But having said this, it's important to know that it is really heavy in terms of data. So we were obviously very lucky with Poland because it has very rich data, which allowed us to be able to go deeper, not only into the sectors, to be able to decompose capital between physical and tangible capital, but also have 18 labor segments. So this is not possible in every situation. So that is a constraint that we will have to take into account when we think of applying this work to other countries. And on the uptake of the model, so CG models are widely used. Obviously, they have a lot of limitations, but despite these limitations, they are a useful tool for policy analysis or scenario analysis. And this is really their main purpose. In the case of Poland, the managed model, for example, is currently being used by the modeling team at the Ministry of Finance. In other countries, it is also largely used. So it is, an analytical tool that can give insight on various policies. And so that's what I would say. Now, in terms of how accurate it is, again, I think it's important to remind our audience that it is a model. So any model is a simplification of reality, but it can give insights. And in CG models in particular, we are comparing a baseline scenario against a simulation scenario. So that baseline scenario means that we are assuming that all things being equal, what could happen if we change this or that variable in the model. So in that sense, I think it's important to consider that into account. So there are some entry points that, or some future developments that would be important to take into account. So Natalie and Marcus have touched up on the new tasks. Again, new tasks, technically it's not very difficult. The question is, how many new tasks are created? So we all know that even when we start as individuals, when we start using AI tools, we are actually doing our job, but we are at the same time within our occupation, we are creating new tasks. But how many new tasks are being created while you are using these AI tools is not very obvious. But in terms of modeling specifications, we have it on our to-do list. And another point maybe to take into account is also, so in our current structure, we also don't take into account the lag between adoption and how, once you adopt, how fast these models are going to be operationalized. So those are some of the points we want to keep in mind.
Great. I have a feeling that it's a discussion that we could continue easily for another hour, but our time in these sessions is limited, and also it's the first presentation of this model. I think there will be others, and there'll be other opportunities to have more discussions about it. So I'm going to have to close this session. And before I do that, I want to thank you, Lulit, Natalie, Marcus, for being here for the presentation and for the great collaboration as well. And I want to thank our audiences, people watching us today and those who will see this session later online. ITU will take a break in the AI for Good session because they will be very busy with the physical meeting of ITU AI for Good in Geneva. But we will come back with more episodes of the series in autumn. And I also want to say big thanks to the communications team at ITU and at ILO who make it possible for us to organize these sessions and to later promote them on our social media. So with this, thanks again, and see you next time.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.